Hey folks, in this lecture we will learn about Kubernetes. Let's first understand the basic problem before we learn Kubernetes. Today, many computer programs do not run on a single computer. They often run on servers, which are powerful computers that stay on all the time and serve many users together, right? For example, when many people open the same website or use the same application, one computer is usually not enough. The work needs to be shared across multiple systems so everything keeps working smoothly. Now, developers create applications, but running and managing those applications is not always easy. An application may stop suddenly, it may use too much memory, or it may crash when too many users come at the same time or log in at the same time. Someone must watch these applications, restart them if they fail, and make sure they are always available. Doing all this work manually is very hard and time consuming, for sure. So, to solve this problem, containers were introduced. A container is simply a small package that includes an application and everything it needs to run. You can imagine a container like a sealed lunchbox that has food, a spoon, and a napkin inside it. Whenever you take this lunchbox, the food is ready to eat. In the same way, a container carries the application with all its requirements so it can run anywhere. However, when you have only one or two containers, life is simple. But in real systems, there can be tens, hundreds of even thousands of containers running together. Now, the real question is who will start them? Who will stop them? Who will restart them if something goes wrong? And who will decide where they should run? Managing all this manually becomes almost impossible. This is where Kubernetes comes in. Kubernetes is like a very smart manager. Its main job is to manage these containers for us automatically. It watches them all the time, checks their health, and takes action when something is not right. If an application stops, Kubernetes brings it back. If more users come, Kubernetes can create more copies of the application. If the load reduces, it can remove extra copies. For example, imagine a busy restaurant kitchen. There are many orders coming in, many chefs working, and many dishes being prepared. If one chef gets sick, the kitchen manager immediately assigns another cook so the work does not stop. If suddenly a lot of customers arrive, the manager brings in more staff, right? If customers leave, the manager reduces staff to save resources. Kubernetes works in a very similar way. But instead of cooks or chefs and dishes, it manages applications and containers. Another important thing is that Kubernetes does not care about one single computer. It works with many computers together or servers. These servers are connected and work as a team. Kubernetes decide which application should run on which computer so that no single system becomes overloaded. This makes application more stable and of course reliable. Beautiful. So the beauty of Kubernetes is that it follows instructions, not just guesses. We tell Kubernetes what we want, such as this application should always be running, or I want 3 copies of this application. Kubernetes then continuously works in the background to make sure the actual situation matches what we asked for. If something changes, Kubernetes fixes it automatically and right away. Behind this powerful system, there's also an interesting background. Kubernetes was originally created by Google, using their real world experiences of running applications on thousands of computers or servers for many years. Google designed Kubernetes to solve the exact problems we just discussed, such as keeping application running, handling failures, and managing load automatically. So in 2014, Google made Kubernetes open source so everyone could use it, improve it, and run application at scale in the same reliable way. So this is a simple explanation of Kubernetes and why it is used to manage and run containerized application automatically. All right, folks, and I'll see you in the next lecture. In this lecture, we will learn why Docker alone is not enough to manage and keep applications running reliably in real-world systems. So let's first understand what is Docker. A Docker is a tool that helps us to create and run containers. A container is like a sealed box that carries an application and everything it needs to run it. Because of Docker, developers can run the same application on different computers without worrying about setup problems or installations. This is a very big advantage, and that is why Docker became popular very quickly. Now imagine you have one computer, and on that computer you run one or two containers using Docker. In this situation, Docker works perfectly. You can start the container, stop it, and even restart if something goes wrong. Everything is under control and you feel comfortable managing it manually. But real systems do not stay small. Over time, applications grow, user increases, and system becomes busy. Now you may have many containers and may have multiple computers working together. At this point, managing everything using only Docker becomes difficult. For example, imagine you own a small shop. In the beginning, you manage everything yourself. You open the shop, handle customers, and close the shop at night. This works fine when the shop is small. But later, the shop grew into the large store and many employees and many sections and many customer, which is great, by the way. At this stage, one person cannot manage everything alone. You need a manager who organizes staff, handles problems, and ensures that everything runs smoothly, right? Docker is like a good worker but not a manager. Docker can run containers, but it does not automatically manage large systems. So, for example, if a container stops suddenly, Docker does not always bring it back automatically in a smart way. If too many users log in at the same time, Docker does not decide by itself to create more containers. If one computer becomes overloaded, again, Docker does not move containers to another computer. Not only that, another issue is the coordination. When many containers are running on different computers, they need to communicate with each other. So managing this communication manually is very hard. This is exactly where Kubernetes comes in as a solution. Kubernetes works on top of containers and takes responsibility for managing them at a higher level. While Docker focuses on running containers, of course, Kubernetes focuses on managing them in an organized and automatic way. It watches the entire system instead of just one container. Kubernetes makes sure applications stay running even if something fails. It automatically restarts failed applications, spread them across computers, and balances the load when users increase or decrease. So, this is a simple explanation of why Docker alone is not enough and how Kubernetes is needed to manage containers. In this lecture, we will learn how Kubernetes is different from traditional Linux servers in managing, scaling, and running applications. In the past, we usually had one Linux server and we install applications directly on it. The application depended on the server's setting, installed software, and systems configuration. If the application stops working, the administrator manually logs in and restarts it. If the server becomes slow, the administrator investigates and fixes it by hand. In this traditional setup, each server is treated as a special case. One server might run one application, another server might run a different one. If traffic increases and more users starts using the application, the usual solution is to buy a new server and repeat all the setup steps. This process takes time and effort and mistakes can easily happen. Later, Docker helped improve the situation. Docker introduced containers, which allowed application to be packed with everything they need to run. Beautiful. This made application easier to move from one Linux server to another. Even after Docker helped a lot, the container was still usually managed by humans. Someone had to start them, stop them, and check if everything were still running. Now, the Kubernetes changes the way servers are treated. Instead of thinking about individual Linux servers, Kubernetes treats all servers as a single pool of resources. This means memory, processing power, and storage are shared together. Applications are no longer tied to one specific server. In traditional Linux servers, the administrator constantly watches the system. Scaling is another big difference. In the traditional approach, scaling means manual work. Someone decides that more users are coming, then manually add servers and install application. In Kubernetes, scaling is automatic. If demand increases, Kubernetes create more application copies. If demand decreases, it removes extra copies to save resources. For example, imagine you are running a delivery business using only one warehouse. Every problem must be handled by a manager watching everything closely. If orders increase, it becomes hard to manage. Now imagine a smart system that automatically opens more counters when customers arrive and closes them when things are calm. Kubernetes works like that smart system, while traditional Linux servers depend heavily on manual supervision. So, this shows how Kubernetes replaces manual server management with an automated, self managing systems compared to traditional Linux servers. I'll see you in the next lecture. In this lecture, we will learn how Kubernetes is different from systemd services in managing and keeping applications running automatically at scale. The reason I'm comparing Kubernetes with all those different services so you will have a better understanding and you will understand the importance of why Kubernetes is needed. So, systemd is a service manager used in Linux systems. A service manager is simply a system that starts programs, stops them, and restarts them if needed. When a Linux server boots up, systemd decides which program should start automatically. These programs are called services. A service can be web application, a database, or any background program that must keep running. With systemd, an administrator creates service rules that say how an application should start and what to do if it stops. For example, systemd can restart a program if it crashes. This works very well on a single Linux server. If the server is healthy, systemd can keep the application alive and running without much trouble. However, systemd works only inside one server. It has no awareness of the other servers. If the entire server goes down, systemd cannot help because it lives inside that particular server. At that point, a human must step in, fix the server, and move the application elsewhere. Systemd does not manage the application across multiple machines. Another limitation of systemd is scaling. Scaling means increasing or decreasing the number of applications copies based on demand. Systemd can start or stop a service, but it does not automatically create multiple copies of an application across many servers. Everything must be planned and controlled manually. Now, here Kubernetes works in a completely different way. Kubernetes is not limited to one server. It manages application across many servers that work together. Instead of only restarting a service on the same machine, Kubernetes can move the application to another machine if one fails. Kubernetes continuously checks the health of applications. If an application crashes, Kubernetes restarts it. All right, another major difference is scale that we discussed earlier. Kubernetes can run many copies of an application at the same time. If more users arrive, Kubernetes increases the number of running copies. If users leave, it reduces them. System D, on the other hand, does not make such decisions automatically across systems. So, folks, this explanation clearly shows the System D manages services on a single Linux server, while Kubernetes manages and scales applications automatically across many servers. And the reason I included this lesson or this lecture in this course is so you know, or if you're wondering why System D can do the same thing as Kubernetes. All right, I'll see you in the next lecture. In this lecture, we will learn what is Kubernetes cluster and how multiple machines work together to run applications. Before understanding a Kubernetes cluster, it is helpful to recall how applications traditionally run on Linux systems. On a single Linux machine, applications are usually managed by Systemd. Systemd is a service manager. When the system starts, Systemd starts those programs. If a program stops, Systemd can restart it. This works well as long as everything stays inside one machine. Now imagine a situation where one machine is not enough. When more users start using an application, one server becomes slow or overloaded. At this point, running everything on a single system becomes risky. If that one machine fails, the entire application goes down. This is where the idea of multiple machines working together becomes important. A Kubernetes cluster is exactly this idea brought to life. A cluster is a group of independent machines, usually called nodes, that are connected through a network and work together. Each node has its own operating system, memory, CPU, and storage, but they cooperate as part of a larger system. Instead of treating machines as separate islands, a cluster treats them as the members of one team. Inside a cluster, work is distributed. Distributions means tasks are shared across machines instead of being handled by one machine. If one node becomes slow or unavailable, other nodes can continue handling the workload. This improves availability, which means the application stays accessible even when problems occur. Another important concept is resource pooling. Pooling means combining resources from all machines into one shared pool. Applications do not care which exact machine provides the CPU or memory. They only see the combined capacity of the cluster. This makes better use of hardware and reduces waste. And this is also called like a shared resources. Now, for example, imagine a call center with many agents. Calls are not tied to one agent forever. If one agent is busy, another agent answers the call. Customers still get support without interruption. The call center behaves like a cluster, and the agents are the nodes. Clusters also improve scalability. When demand increases, the machines can be added to the cluster, and when demand decreases, the machine can be removed. The system adapts without rebuilding everything from scratch. A Kubernetes cluster applies this cluster idea to applications. It provides a structured way for machines to cooperate, share resources, and keep applications running reliably. Kubernetes uses the cluster as its foundation. All right, so this is a simple explanation of what is a Kubernetes cluster and why multiple machines are used together to run applications reliably. In this lecture, we will learn about the high level and low level views of Kubernetes. In Kubernetes, a view means a structured way of understanding the system by choosing how much internal detail you want to see. Kubernetes is a large and complex system, so studying it from a single angle makes learning difficult and confusing. The purpose of Kubernetes views is to make learning and operating the system easier. A high level view helps you to understand what Kubernetes does and how it behaves as a system, such as running applications, keeping them available, and scaling them. A low-level view helps you to understand how Kubernetes actually works internally, including its components, decisions, and processes. Okay, so let's start learning about a high-level view of Kubernetes. The high-level view means looking at the system from the outside. At this level, we care about what the system does, not how it does it. We observe outcomes, rules, and behavior. This view hides internal complexity so the system feels simple to use. It answers questions like, is the application running? Is it stable? Is it scaling? It's more like questions from a manager. This expected situation is called the desired state, which simply means the condition you want the system to stay in. In this view, Kubernetes decides where they should run and handles everything in the background. So it's focused only on results and not on technical steps. Now we shift to the low level view, which explains how Kubernetes achieves these behavior. At this level, we see internal components working together. One key component is the control plane. The control plane is the decision making part of Kubernetes. It observes the system and issues instructions. Within the control plane, the API server plays a central role. The API server is the entry point where requests are received. Every command or configuration passes through it. Another component is the etcd, which is a distributed key value store. A key value store is a database that saves information in pairs, such as names and values. etcd stores the entire cluster state. The scheduler is another low-level component. Scheduling means selecting an appropriate node to run an application. The scheduler examines the resource availability, such as CPU and memory, before making a decision. These choices are invisible at a higher level but critical internally. On each machine, a component called a kubelet runs. The kubelet communicates with the control plane and ensures the assigned applications actually run. It interacts with the container runtime, which is the software responsible for restarting or starting the containers. Networking is also part of low-level view. Kubernetes also creates virtual networks, which means it connects applications across different machines and allows them to communicate as if they were running on a single system. At this level, Kubernetes also handles storage, checks whether applications are healthy, and restarts them when needed. So all of these actions happen automatically in the background, and there is no need to worry about the details right now, because these internal parts will be learned step by step in the later lectures. So, in simple words, the high level view helps users to think in terms of goals and results, whereas the low level view explains how those goals are achieved through coordinated components. Both views describe the same system but from different angles. I'll see you in the next lecture. In this lecture, we will learn what is a pod in Kubernetes and why it is the basic unit for running applications. When Kubernetes runs an application, it does not manage individual containers by themselves. It places containers inside a structure called a pod. A pod is the smallest unit that Kubernetes understands. This means Kubernetes creates a pod, watches the pod, and manages the pod. The container always lives inside that pod. You can think of a pod as a small space where one or more containers live together. Kubernetes never looks at the container alone. It always looks at the pod that holds the container. If the pod stops, everything inside it stops. If the pod is restarted, all containers inside it restarts together. Now let's understand why Kubernetes uses pods instead of containers directly. In real applications, there is often more than one part. One part may handle user requests, and another part may help with logging, monitoring, and configuration, right? These parts must stay very close to each other and must always run together. A pod keeps these parts together as one unit. Inside a pod, all containers share the same network. This means they use the same IP address and can communicate easily without complex setup. They can also share storage, which means they can read and write the same files. This makes cooperations between containers very easy and safe. A container alone only knows how to run a program. It does not know anything about where it should run, how it should restart, or how it should stay connected with other parts of the application. So Kubernetes needs something bigger than a container to manage all this, and that bigger unit is the pod. Another important reason is the control. Kubernetes places pods on machines, not containers. It checks if pods are healthy. If something goes wrong, it replaces the pod. The containers inside follow the pod's life. This gives Kubernetes clear and consistent control. For example, let's take a small office room. The people inside the room work together and share the same space, internet, and files. So you do not manage each person separately, right? You are the property manager or the resource manager, so all you care about is managing the room. So you manage the room as a whole. In the same way, Kubernetes manages the pod, not individual containers. So, in simple words, a container is responsible for running a single program, while a pod is responsible for managing how the program runs inside Kubernetes. A container focuses on execution, but a pod focuses on organization and control. Kubernetes never manages containers alone, it always manages them through pod. That is why pods exist as a layer above containers. The goal of this lecture is to clearly connect Kubernetes terminology with familiar Linux concepts so that Kubernetes feels easier to understand. Linux is an operating system, which means it is the core software that controls computer hardware, run processes, manages memories, handle files, and controls networking, right? Kubernetes is not an operating system. It is a platform that runs on top of Linux operating system. Kubernetes is installed on Linux machine and uses Linux features to manage and coordinate applications. Once this difference is clear, mapping Kubernetes terms to Linux concept becomes much easier. In Linux, a process is running program controlled by the kernel. Every process consumes CPU, memory, and system resources. In Kubernetes, basic execution unit is a container which usually runs a single main process. Containers rely on Linux kernel features like namespaces and control groups to isolate processes and limit resource usage. Linux uses systemd services to manage long running processes or daemons. A systemd service defines how a process starts, stops, and restarts on one machine. Kubernetes introduces the pod, which serves a similar purpose but at a higher level. A pod defines how one or more containers run together. Unlike a systemd service, a pod is not fixed to one machine and can be recreated elsewhere. A Linux server is a physical or virtual machine with its own operating system. In Kubernetes, this machine is called a node. A node provides resources like CPU, memory, storage, and networking for running pods. Multiple nodes together form a cluster, extending the idea of multiple Linux servers into a shared environment. Linux stores configuration in files, often under directories like /etc, right? Now, Kubernetes replaces static configuration files with config maps and secrets. Config maps hold non-sensitive settings, while secrets store sensitive data such as passwords. These configurations are added to pods when they start running. They are not permanently written inside the application files. Linux controls access using users, groups, and permissions. Kubernetes maps this concept using RBAC, or role based access control. RBAC defines which users or services can read, create, or modify resources inside the cluster, similar to how sudo and file permissions work in Linux. In Linux networking, applications listen to a specific IP addresses and port numbers so they can receive traffic. Kubernetes uses services to give applications a stable network address. Even if pod restarts or change, the address stays the same. This means we do not need to keep track of individual pod IP addresses. Moreover, Linux administrators view logs using tools like journal control. Kubernetes associates logs with containers and pods, but the purpose remains the same: observing behavior, errors, and system health. So, in simple words, Kubernetes does not replace Linux concepts. It builds on them, extends them across multiple machines, and automates their management. So, understanding this connection helps Linux administrators use what they already know. They can manage Kubernetes clusters without learning everything from scratch. I'll see you in the next lecture. In this lecture, we will go over some common myths and misconceptions about Kubernetes that often confuse beginners. All right, one common myth is that Kubernetes is just a Docker. This is not true. Docker is used to build and run containers, while Kubernetes is used to manage those containers across many machines. Docker handles packaging, but Kubernetes handles coordination and control. All right. Another misconception is that Kubernetes replaces Linux, which we have already talked about. Kubernetes does not replace Linux at all. Linux is still the operating system running on each machine. Kubernetes runs on top of Linux and uses Linux features to function properly. All right. Many people believe Kubernetes is only for very large companies. This is incorrect. Kubernetes can be used on a single machine for learning and testing, and it can also run large production systems. Another misconception is that Kubernetes removes the need for system administrators. In reality, Kubernetes changes the role of system administrators. Instead of manually fixing issues, administrators design rules and let Kubernetes handle problems automatically. All right, another myth is that Kubernetes prevents all failures. Failures still happen. Machines can crash and networks can break. Kubernetes does not stop failures, it manages them in a controlled and automatic way. There's also a belief that Kubernetes is too complex to learn. Kubernetes seems complex when learned without Linux basics. With a strong Linux background, Kubernetes concept becomes easier and more logical. Plus, when you are taking this course, the entire course will teach you everything about Kubernetes as if you are learning from scratch. And you will learn so much about Kubernetes by the time you finish this course. All right, another misconception is that pods are permanent. Pods are not permanent objects. They can be destroyed and recreated at any time. Kubernetes accepts pod to be temporary or replaceable. Another misconception is that Kubernetes automatically optimizes everything without configuration. Kubernetes follows instructions given by the user, not without any configuration. So, poor configuration can still cause issues. Okay, another thing is that people believe that Kubernetes runs application faster. That's not true. Kubernetes does not increase application speed. It improves reliability, availability, and management, not raw performance. Another misconception is that Kubernetes networking works like traditional server networking. Kubernetes networking is abstracted and behaves differently, which requires a new way of thinking. So, folks, clearing these myths is important because a wrong understanding causes frustration. I hope this lecture helps you clear misunderstanding and myths and makes Kubernetes easier to understand and learn with me throughout the course. Let's go right ahead. Hey folks, in this lecture we will learn about an important benefit of this course, and that is how this course prepares you for some of the most valuable Kubernetes certifications that can help you grow your career and prove your skills in real world environments. This course is designed in a way that matches what companies expect from a Kubernetes professional, and it helps you build a strong understanding step by step. The first certification this course covers is Certified Kubernetes Administrator, in short CKA, which is one of the most recognized certifications for system administrators. And it focuses on how to manage clusters, work with nodes, handle networking, storage, and troubleshoot issues in real environment. And in this course, you will learn all of these through hands-on practice, like setting up clusters with ADM, working with pods and deployments, scaling application, and fixing real problems. Along with that, this course also prepares you for the Certified Kubernetes Application Developer, in short, CCAD or CKAD, which is focused on building and managing applications inside Kubernetes. And here you'll learn how applications run inside pods, how deployments work, how updates happen, and how to manage configurations using config maps and secrets. Finally, this course also introduces you to the Certified Kubernetes Security Specialist, in short CKS, where you start understanding security concepts like access control and permission using RBAC, and how misconfiguration can break applications, which gives you strong base for secure environment. So by the end of this course, you are not just learning theory, you're building the exact skills that align with these certifications and prepare you for real job roles. And if you wanted to learn more about the certification, how they are structured, what kind of exams you're going to get, I have all these three courses certifications on my Udemy profile. You can definitely go and take those courses to make yourself more familiar and make yourself ready and prepared to take the certifications exams. So, good luck to you. Let's start a new section where we go deeper into the architecture of Kubernetes. So we start by learning the control plane and worker nodes and how they work together. In a Kubernetes cluster, all servers do not perform the same role. Some servers are responsible for managing and deciding, while other servers focus on running the applications. This separation keeps the cluster stable and easier to manage, especially as the environment grows. The servers that handle management tasks is known as control plane. The control plane acts as a brain of the cluster. It keeps track of the current state, accept instructions, and make decisions about where applications should run. These servers handle coordination tasks and do not run user applications. The servers that run applications are called worker nodes. You may notice we also call a worker node a server machine because it is a full Linux server with its own operating system, CPU, memory, and storage, and it runs application workloads just like any other server. The control plane decides which worker node should run the application. When an application needs to run, it is placed on one of these worker nodes, and that node is responsible for keeping it running. Within the control plane, responsibilities are divided. One part accepts requests, another part stores cluster information, and another part decides placement. These components work together to maintain order and consistency across the cluster. Now, worker nodes also have their own duties. They run containers, report health information, and follow instructions from the control plane. They do not make cluster-wide decisions. Their job is just simply execution. For example, imagine a company with a main office and several branch offices. The main office decides what works needs to be done and how it should be done. It assigns tasks like handling customer requests, processing orders, and managing schedules. It also checks progress and makes sure rules are followed. The branch offices receive these tasks from the main office. They focus on completing customer orders and daily operations. They do not make decisions or change company rules. If one branch office has a problem, the main office assigns the work to another branch. This keeps the work moving without interruption. Because tasks are clearly divided, the whole company works smoothly. So, folks, this simple explanation of how the control plane worker nodes work together to manage application in a Kubernetes cluster. In this lecture, we will learn about etcd or etcd and its role inside Kubernetes. Etcd is a distributed key value store, which means it is a database that saves information in pairs, where a key is a unique name and the value is the data linked to that name. Kubernetes uses etcd to store all cluster data. So anything that exists in the cluster, such as applications, settings, or system date, is stored inside etcd. Because of this, etcd is called the single source of truth in Kubernetes. This means Kubernetes fully trusts etcd, and whatever data is written there is treated as a correct and final state. If something is not stored in etcd, Kubernetes does not recognize it as part of the cluster. An important design rule is that only the API server is allowed to communicate directly with etcd. No other Kubernetes components can read or write data to it. This design keeps the cluster secure and consistent because all changes go through one controlled entry point. etcd itself is built as a distributed system, which means it can run on multiple servers at the same time. These servers work together so that data remains available even if one server fails. Each etcd server is called a member, and a group of members working together is called an etcd cluster. In production environment, Kubernetes usually runs etcd as a cluster to avoid data loss. To keep data consistent across members, etcd uses a consensus algorithm called raft. Consensus means all members must agree before data is changed. Raft ensures that every write operation is approved by the majority of members before it is saved. Inside Raft, one member acts as a leader, and all write requests go through this leader. The remaining members act as followers and copy data from the leader. If the leader fails, another member is actually elected, which keeps the system running without manual intervention. etcd stores data in a structured called key space. You think of the key space like directories and subdirectories in Linux. Each key looks like a path, and Kubernetes uses these paths to store objects in an organized way. These paths include information such as namespace and the type of object. So pods, services, and configuration data are stored under separate and clearly defined paths. Because of this structure layout, Kubernetes can quickly find the required data and the cluster remains consistent and reliable. etcd supports basic data operations such as create, read, update, and delete. Every change made to Kubernetes object is translated into one of these operations in etcd. For example, creating a pod causes Kubernetes to store its information in etcd. Checking the pod status means reading that information, and updating or removing the pod causes etcd to update or delete and stored data. Another powerful feature of etcd is watch, which allows components to receive updates whenever data changes. Instead of checking again and again, etcd notifies the API server about changes. and the API server informs other components, allowing Kubernetes to react immediately. etcd also keeps a revision number for every change made to the data. Each update increases this number, which helps Kubernetes track changes in the correct order, just like a version control. For example, when a pod is created, etcd saves it with a revision number, and when it is updated later, the number increases. Kubernetes uses these numbers to understand which change happened first and which came later. Another important concept is leases, which work like timers attached to the stored data. As long as the timer is active, the data remains valid. If the timer expires, the data is removed automatically. Kubernetes uses this mechanism to detect failures, such as when a node stops responding. etcd also supports transactions, which means multiple changes can be grouped into one single action. Either all changes are applied together or none of them are applied. If something goes wrong, everything is canceled. This prevents half-done updates and keeps the cluster data correct and consistent. Security is also a core part of etcd design. etcd encrypts data while it moves between components and allows only trusted components to connect. Kubernetes controls access using certificates so that only the API server can write important cluster data. To protect data from crashes, etcd writes every change to disk using a special log before applying it. If a server crashes, etcd can recover data using this log. For better performance, etcd uses data in memory so it does not need to read from disk again and again, which reduces disk usage and improves response time. etcd also supports snapshots, which are full copies of the data taken at a specific time. Administrators use these snapshots for backup and disaster recovery. If etcd data is lost and no snapshots exist, the cluster cannot recover. That's why etcd backup is one of the most important operational tasks. etcd itself does not understand Kubernetes concept like pods or services. It only stores structured data in a readable way. All Kubernetes logic exists outside of etcd. In simple words, etcd acts like the memory of the cluster. The API server writes what Kubernetes wants to happen, and etcd remembers it permanently. Without etcd, Kubernetes cannot track state, recover from failures, or coordinate its components, which makes etcd one of the most important parts of Kubernetes architecture. In this lecture, we will learn how the API server and the scheduler work together inside Kubernetes and how their coordination allows the cluster to function in an organized and controlled way. These two components are tightly connected, and understanding their relationship helps you to clearly see how Kubernetes makes decisions and takes action. The API server is the main communication center of the Kubernetes. Every request, whether it comes from a user, a command line tool, or an internal Kubernetes components, must go through the API server. When you ask Kubernetes to create an application, scale it, or check its status, that request is first received by the API server. This makes the API server the only trusted entry point into the cluster. The API server works using standard HTTP requests. These requests follow a structured format, which allows Kubernetes to treat everything as data. When a request arrives, the API server first checks who is making the request. This step is called authentication. It verifies identity using certificates, tokens, or service accounts. If identity is not confirmed, the request stops there. Once identity is verified, the API server checks permissions. This step is called authorization. Here, Kubernetes uses role-based access control, also known as RBAC. RBAC ensures that users or services can only perform actions when they are allowed to perform. If permissions are missing, the request is rejected. After authorization, the API server applies admission control. Admission controllers are internal mechanisms that can modify or block requests. For example, they can enforce security rules, apply defaults, or prevent unsafe configuration. Only after passing this stage, the request is considered acceptable. At this point, the API server stores the approved request in etcd, which is the cluster data store. Writing to etcd means the desired state of the cluster has officially changed. The API server then responds back to the requester confirming that the request has been accepted. Now, this is where the scheduler enters into the picture. The scheduler is a Kubernetes component responsible for deciding where the application should run. The scheduler does not act on its own, by the way. It continuously watches the API server for new objects that need a place to run. For example, it looks for pods that are created but do not yet have a server, and then decides which server should run them. So, when the scheduler notices a new pod without a node assignment, it starts its work. The scheduler responsibility is to decide where the pod should run. This decision is not random. The scheduler carefully checks all available worker nodes in the cluster. The scheduler checks resource availability, such as CPU and memory, on each node. It also checks constraints defined in the pod specification, such as node selectors, affinities, and toleration. Constraints are rules defined in the pod specification. Node selector is a rule that limits the pod to specific servers. Affinity describes preferred placement near a certain pods or nodes. Toleration allows the pod to run on servers with special restrictions. All these constraints guide the scheduler to select a suitable server. After filtering out unsuitable nodes, the scheduler ranks the remaining nodes using scoring rules. These rules help to determine the best possible placement based on efficiency and balance. Once the best node is selected, the scheduler writes this decision back to the API server. The API server then records this binding information in etcd. This update changes the state of the pod from unassigned to assigned. Other components in the cluster can now see this update through the API server. The API server continues to act as a central messenger. It notifies the appropriate worker node that the pod has been assigned to it. The worker node then takes responsibility for starting the pod. Throughout this process, the API server and scheduler remain synchronized. In simple words, the API server provides a consistent view of cluster state, while the scheduler makes placement decision based on that view. Let's take a simple example to understand this complete process in a simple way. Imagine you have an office where many people submit work requests every day. No one is allowed to directly go to an employee and assign work. Every request must first go to one central place. This central place requests the API server in Kubernetes. When a request arrives at his desk, the first thing it does is check who sent the request. This is similar to authentication, where identity is verified. If the person is not recognized, the request is rejected immediately. If the identity is valid, the desk then checks whether this person is allowed to request this type of work. This matches authorization, where permissions are verified using defined rules. Once the request is accepted, the desk carefully records it in the office system. This recording step is like writing data into etc, where Kubernetes stores the official state of the cluster. At this moment, the request becomes part of the system's truth, and everyone in the office can now see that this work needs to be done. Now, the desk does not decide who should do the work. The responsibility belongs to the manager. Now, the office manager here represents the scheduler. The manager continuously watches the system to see if there are new unassigned tasks. When the manager notices a new task, it starts evaluating all available employees. The manager checks which employees are free, which ones have the right skills, and which ones are already overloaded or a lot going on in their plate. This is similar to the scheduler checking CPU memory and constraint on worker nodes. The manager then chooses the most suitable employee for the task. After making that decision, the manager does not directly inform the employee. The decision is sent back to the central desk. This reflects how the scheduler writes his decision back to the API server. The desk records this assignment in the office so it becomes official and visible. Once the assignment is recorded, the desk informs the selected employee. This is like the API server notifying the worker node that the pod has been assigned to it. The employee then starts working on the task, just as the worker node starts running the application. Throughout this process, the desk and the manager stay in constant coordination. The desk handles identity rules and records, while manager focuses only on choosing the right person for the job. I hope you understand how API server and the scheduler work together inside Kubernetes and how their coordination allows the cluster to function in an organized and controlled way. I'll see you in the next lecture. In this lecture, we will learn about kubelet and kubeproxy. In a Kubernetes cluster, decisions are made by the control plane, but real work happens on worker nodes, right? Kubelet and kubeproxy are the two most important components that live on every worker node. Without them, worker nodes would just be normal Linux servers with no Kubernetes behavior. The kubelet is an agent that runs on each worker node. An agent means a program that listens, acts, and reports back. The kubelet's main responsibility is to make sure that the containers assigned to its node are actually running and healthy. The kubelet continuously communicates with the API server. It does not make decisions on its own. It asks the API server what pods should be running on this node. The API server responds with the desired state, meaning which pod and container should exist on that worker node. Once the kubelet receives this information, it takes action. It checks whether the required containers are already running. If they are not running, the kubelet instructs the container runtime to start them. A container runtime is the software that actually creates and runs containers, such as CRI-O or Docker. The kubelet does not directly run containers itself. It uses the container runtime interface, often called CRI. CRI is a standard interface that allows Kubernetes to work with different container runtimes without changing its core logic. This makes Kubernetes flexible and modular. After starting containers, the kubelet constantly monitors them. It checks their status, resource usage, and health. Health is verified using liveness probes and readiness probes, which are defined in the pod configuration. A liveness probe checks if the container is still running properly. If the liveness probe fails, kubelet restarts the container. A readiness probe checks if the container is ready to receive traffic. If the readiness probe fails, traffic is stopped until the container becomes ready again. So these probes tell kubelet whether a container is alive and whether it is ready to receive traffic. If a container crashes or becomes unhealthy, the kubelet reports the information back to the API server. Based on the desired state, Kubernetes may restart the container or replace the entire pod. The kubelet ensures that the actual state on the node matches what the API server expects. Now let's move to kubeproxy, which solves a completely different problem. While kubelet focuses on running containers, right? Kube proxy focuses on networking and traffic flow. In Kubernetes, applications are accessed through services. A service provides a stable network endpoint even when pods are created, destroyed, or moved. Kubeproxy is responsible for making these services work on each worker node. Kubeproxy runs on every worker node and watches the API server for changes related to services and pods. When a service is created or updated, Kubeproxy receives this information and updates network rules on the node. Technically, Kubeproxy works by configuring IP tables or IPVS rules. These are Linux networking mechanism used to route traffic. IP tables work by defining packet filtering and forwarding rules. IPVS is a more advanced load balancing mechanism that performs better at scale. When traffic arrives at a worker node for a service, kubeproxy ensures that the traffic is forwarded to one of the correct pods. It does not care which pod exactly, as long as the pod belongs to that service. This enables load balancing, which means distributing traffic evenly across pods. Kubeproxy does not inspect application data. It works only at the network level. Its job is to move packets correctly and efficiently. If a pod is removed or becomes unavailable, kubeproxy updates its rule so traffic is no longer sent to that pod. Let's take a simple example to understand this complete process in a simple way. Imagine you have a large warehouse that receives orders and delivers goods every day. This warehouse represents a worker node in Kubernetes where actual work is done. Inside the warehouse, there is a supervisor whose job is to make sure workers are present, assigned tasks, and doing their job correctly. This supervisor represents the kubelet. The kubelet continuously checks instructions from the central office, which in Kubernetes is the API server. It does not decide what kind of work should exist, it only follows the instruction it receives. When the central office records a new order, it sends instructions to the warehouse supervisor. This is similar to the API server telling the kubelet that the new pod should run on the worker node. The kubelet then checks whether the required workers, which represents containers, are already active. If they are missing, the kubelet asks the container runtime to start them. Once the workers are active, the supervisor keeps checking their health. If a worker stops working to become unresponsive, the supervisor reports this issue back to the central office. This shows how kubelet monitors container health and reports status back to the API server. Now, inside the same warehouse, there is another role. This role manages the entry and exit of delivery trucks. This role represents kube proxy. Delivery trucks are like network requests coming from users. Kube proxy ensures that each truck is directed to the correct loading area where goods are handled. The loading area represents the pods, and the warehouse address represents a service. Even if a loading area change or move, the warehouse address stays the same. Kubeproxy updates the routing rules so trucks always reach an active loading area. If the loading area closes or a new one opens, kubeproxy immediately updates the routing paths. This matches how kubeproxy adjusts network rules when pods are added or removed. Now it's time to understand how Kubernetes makes decisions. Kubernetes does not guess, and it does not act randomly. Every decision is the result of defined components, stored state, and continuous evaluation. Kubernetes works on a declarative model. Declarative means you do not tell Kubernetes how to do something step by step. You tell it what you want, and Kubernetes figures out how to achieve it. Beautiful. This What you want is called the desired state. The desired state is always stored in etcd through the API server. The API server is the starting point of every decision. When a new object is created or an existing one is changed, the API server validates it, applies policies, and stores it in the etcd. At this point, Kubernetes has an official record of what should exist in the cluster. Once the desired state is stored, Kubernetes relies on a set of background processes called controllers. A controller continuously compares two things: the desired state stored in etcd and the actual states observed in the cluster. This comparison loop in called the control loop. If the controller finds a difference, it decides that action is required. For example, if three pods are desired but only one exists, the controller decides that one more pod must be created. It does not create the pod directly. It sends a request to API server to update the state. When a pod exists but has no assigned node, the scheduler becomes involved. The scheduler watches the API server for pods in an unassigned state. It evaluates available nodes using filtering and scoring phases. Filtering removes nodes that cannot run the node due to missing resources or constraint. Scoring ranks the remaining nodes based on efficiency and balance. After the scheduler selects the best node, it records its decision by updating the pod object through the API server. This decision is again stored in etcd, making it part of the official cluster state. Once a pod is assigned to a node, the kubelet on the node notices that assignment. The kubelet does not decide to run the pod, it simply acts on the recorded state. It pulls container images, starts containers using the container runtime, and monitors their health. Health checks plays a key role in decision making. Kubernetes uses liveness probes, readiness probes, and startup probes to understand container behavior. These probes feed information back into the control loop. If a probe fails, Kubernetes decides whether to restart a container or replace the pod. Kubernetes also makes decisions based on events. Events are structured records of what happens inside the cluster. Controllers and nodes generate events, and these events help Kubernetes understand failures, delays, and changes. Resource management is another decision factor. Kubernetes uses resource requests and limits to understand how much CPU and memory a pod expect to use. Scheduling and eviction decisions depends heavily on these values. If a node runs out of memory, Kubernetes may decide to evict certain pods. Policies also influence decisions. RBAC policies control who can do what. Admission controllers enforces rules before objects are accepted. Taints and toleration influences where pods are allowed to run. All these rules shape how decisions are made. So the most important thing is that Kubernetes makes decisions continuously, not just once. The system constantly reevaluates the cluster. Even after decision is made, Kubernetes keeps checking whether the outcome still matches the desired state. Now let's understand all this process with a simple example. Imagine you define an application that should have two running pods. The API server stores this request in etcd. A controller notices that zero pods exist and decides to create two pods. The scheduler evaluates nodes and assigns each pod to a suitable node. The kubelet starts the containers and reports status. Later, one pod crashes. The controller detects that only one pod is running, while two are desired, and decided to create a replacement. Traffic is adjusted automatically, and the system returns to the desired state without manual action. This is how Kubernetes makes decisions by observing state, comparing it continuously, applying rules, and acting through well defined components in a synchronized flow. We have learned Kubernetes concepts and architecture in detail, and now it's time to move toward practice. Before starting hands on work, it is important to understand how Kubernetes is practiced locally, because learning on a local system builds confidence and clears confusion before moving to production environments. Kubernetes is usually designed for multiple servers, but for learning and testing, it can also run on a single system. Local practice allows us to understand behavior, commands, and workflows without needing a full data center setup. This is where tools like Minikube and KubeADM or admin come in. Minikube is a tool designed specifically for learning and development. It creates a small Kubernetes cluster on a single system or node using a virtual machine. Minikube hides most of the complexity and allows us to focus on Kubernetes concepts instead of infrastructure setup. When Minikube runs, it automatically sets up the control plane and worker components together. This makes it ideal for beginners because the environment is ready quickly and common Kubernetes features work out of the box. Minikube is mainly used to practice pods, services, deployment, and basic troubleshooting. KubeAdmin, on the other hand, is a tool used to build Kubernetes cluster in a more realistic way. It follows the same process used in the production environment. KubeAdmin does not hide complexity. It exposes how Kubernetes components are initialized and connected. With KubeAdmin, we manually prepare the system, install required packages, and initialize the control plane. Worker nodes are then joined using a secure command. This process helps us to understand how clusters are formed and how components communicate. So, in this course, we will use both Minikube and KubeAdmin to gain better understanding. Minikube will help us to build basic confidence, while KubeAdmin will help us gain deeper operational knowledge. Together, these tools create a strong bridge between theory and real world Kubernetes usage. So, let's fasten your seatbelt and get ready to begin hands on practice with Kubernetes. In this lecture, we will learn about YAML and why it is important in Kubernetes. In Kubernetes, almost everything we create, like pods, deployments, and services, are written in YAML. So, learning YAML is necessary to tell Kubernetes what we want to do. YAML stands for YAML Ain't Markup Language, and it is a human readable format used to store and organize data in a simple and structured way. The name may sound a little funny, but it tells us something important because YAML is not about writing complex markup like HTML. It is about representing data in a clean, readable, and easy to understand format for both humans and machines. It looks very close to plain English, which makes it easier to read compared to other formats. In Kubernetes, YAML is mainly used as a configuration file, which means it tells Kubernetes how an application should run, how many copies it should exist, which image should use, and how different components should connect with each other. One of the best things about YAML is that it removes unnecessary symbols. You will not only see curly braces or brackets like in JSON. YAML uses simple spacing and indentation to show relationship between data. YAML is built on three simple ideas: key, value, and structure. A key is like a name, and the value is the information linked to that name. For example, in Kubernetes, if we define a key called name and give it a value like web app, it means we are naming our application. YAML uses a colon to separate the key and value, and it uses spaces, not tabs, to organize the structure. Indentation plays a very important role in YAML because it defines the hierarchy, which means it shows how different elements are related to each other. For example, in Kubernetes, if we define a deployment, Then inside it, we define containers. And inside containers, we define image and ports. All of this is controlled by spacing. If the spacing is wrong, Kubernetes may not understand the configuration correctly. So we must be careful with indentation. YAML also represents lists, which are groups of items. In Kubernetes, this is very common. For example, if a pod has multiple containers, each container is written as a separate item in a list. Each item starts with the dash, which means it's a part of a group. This makes it easy to define multiple components in a clean and readable way. Another useful feature of YAML is components. A component is a line written only for humans to understand, and Kubernetes ignores it. Comment starts with the hash symbol. In Kubernetes YAML files, comments are often used to explain what a certain section does, which helps other team members to understand the configuration easily. In Kubernetes, YAML is used to define the desired state of the system, which means you describe what you want, and Kubernetes ensures that the system matches that description. This makes YAML a key part of how Kubernetes manages and controls applications inside the cluster. Imagine you want to run a web application using IMf&x. Instead of running commands again and again, you write a YAML file that defines the deployment with the IMf&x image and sets the number of replicas to 2. Once you apply that file, Kubernetes automatically creates the pod, keeps them running, and replaces them if something fails. So this is a simple explanation of YAML and its role in Kubernetes. I will see you in the next lecture. In this lecture, we will learn about the prerequisites and system requirements needed before practicing Kubernetes locally. This step is very important because Kubernetes depends heavily on system resources, and without proper requirements, the setup may fail or behave slowly. Kubernetes is designed to manage multiple applications at the same time. Because of this, it needs enough RAM, CPU, and storage to work smoothly. Even for local practice, lightweight systems are often not sufficient. The minimum recommended RAM for local Kubernetes practice is 4 gig. Because Kubernetes runs several background components, such as the API server, scheduler, controller manager, and etcd. These components constantly run and consume memory. If RAM is less than 4 gig, the cluster may start but will become slow or unstable. CPU requirement is also important. Kubernetes performs scheduling, health checks, and monitoring continuously. At least 2 CPU cores are required for smooth operation. With only one core, the system may struggle to handle container workloads and background services together. Storage plays an important role as well. Kubernetes stores images, logs, configuration data, and cluster state. A minimum of 20 gig SSD storage is recommended. SSD is preferred because Kubernetes performs frequent read and write operations, and HDD storage can slow down the cluster. The operating system should be a 64-bit Linux system. Kubernetes does not support 32-bit systems. Linux distributions such as CentOS, Rocky Linux, or similar enterprise-friendly systems are suitable for practice. Virtualization support must be enabled in the system BIOS. Tools like VirtualBox or VMware require hardware virtualization to run virtual machines properly. Without this, Kubernetes nodes inside virtual machines may not start. A stable internet connection is required during setup. Kubernetes downloads container images and packages from online repositories. Without internet access, installation steps may fail. The system must support container technology. Docker or another container runtime is required because Kubernetes runs applications inside containers. If the container runtime is missing or misconfigured, Kubernetes cannot function. Basic Linux command line knowledge is also a prerequisite. Kubernetes setup involves running commands, editing configuration files, and checking logs. Comfort with terminal usage helps avoid confusion. So these requirements ensure that Kubernetes runs reliably during practice. Meeting these prerequisites helps to avoid frustration and allows you to focus only on learning Kubernetes concepts rather than troubleshooting system limitations. In this lecture, we are going to download and install VirtualBox, which is the virtualization software that we will use to create our Linux virtual machine. For this, we open our browser and go to the website by typing virtualbox.org in the address bar. Once the home page loads, you can see a blue download button, and we click on it to continue. Now we are on the downloads page where VirtualBox provides different installation files based on the operating system. Since we are using the Windows operating system, that's why we click on the option that says Windows Hosts. As soon as we click on it, the download starts, and you can see the progress in the top right corner of the browser. Let's wait for the file to complete downloading. After the file finishes downloading, now it's time to run the installer. Now you can see the VirtualBox logo appear on the screen, and this tells us that the installer is loading. Let's wait for a moment until the setup window fully opens. Once it loads completely, you can see a welcome message. Now let's click on the next button to continue the process. After clicking next, the license agreement page appears. Here you need to accept the terms so the installation can continue. Let's accept the terms of the license agreement and then click next again. The next screen shows the installation settings. We don't need to change anything here because the default options work fine. So once again, we click next. Now you may see a warning message telling you that your network might disconnect for a short time during installation. This is normal, so click yes to continue. After that, another window appears, showing a few optional settings such as adding VirtualBox to the Start menu and creating a desktop shortcut. These options are already selected by default, so we don't need to change anything here. You can simply click the Next button. Now the installer shows a screen that says Ready to install, and this means everything is set, and we can begin the installation. Click the Install button. Once the installation starts, it may take a few minutes to complete. During this time, we just wait and let the process finish. Now the installation is done, and a final window appears confirming that VirtualBox has been successfully installed. You can also see a checkbox saying Start Oracle VirtualBox. We keep that checked and then click the Finish button. After clicking Finish, VirtualBox automatically opens, and now you can see the main VirtualBox interface on your screen. This confirms that the installation successfully completed and VirtualBox is ready to use. So this is a simple explanation of how we download and install VirtualBox step by step in a clear and easy way. See you in the next lecture. In this lecture, we will learn how to set up a virtual machine and install Linux CentOS inside VirtualBox step by step. Let's get started. Before we start, we will first download the CentOS Linux ISO file. For this, we will open our web browser, and in the address bar, we type centos.org. As soon as we press enter, the official CentOS website opens. Here on the home page, we can see different options at the top, and one of them is the download button. So we move our mouse to that button and click on it. As soon as we click download, we are taken to a new page where we can see different versions of CentOS Linux available. On this page, the latest version is shown, and that is CentOS Stream 10, so we select it. Below that, we see several download categories, but The one we need is the ISO file because this file will allow us to install Linux inside our virtual machine. So we click on the button labeled Mirrors under the ISO column. After clicking the Mirrors button, the download starts, and you can see the progress in the top right corner of the browser. Since the file size is large, around 8.5 gig, it may take some time to finish depending on your internet speed. So let's wait until the download is complete. Once the file finishes downloading, we can also open the folder and confirm that the file is there. As you can see, the file name appears as CentOS Stream 10 latest x 8664 DVD 1.iso. And this is exactly what we need for installation. Now it's time to start creating the virtual machine and connect this ISO file to install Linux inside it. For this, we open VirtualBox, which is already installed on our system. To create our virtual machine, we start by clicking on the New button in VirtualBox. As soon as we click it, a new window appears where we will set up the basic information for our virtual machine. In the first field, we type a name for our system. Here we are naming it, for example, CentOS Linux, so we can easily identify it later. Just below the name, we can see the location, where VirtualBox will save all files related to this virtual machine, and we leave it as default. Next, we move to the operating system selection. Since we are installing Linux, the OS type is automatically set to Linux. And under OS distribution, we select Red Hat because CentOS is based on Red Hat Linux. Just below this, we also confirm that the OS version shows Red Hat 64-bit, which is correct for the CentOS ISO we downloaded earlier. Now we move to the next section where we configure the hardware settings for our virtual machine. On this screen, we adjust the memory and CPU values according to what our system can support. Here, the memory slider is increased to around 4 gig, which is a good amount for a smooth Kubernetes experience, and then the CPU count is changed from 1 core to 2 cores to give the Kubernetes better performance. These options can be changed depending on how powerful your actual computer is, but this setup works well for most users. Then we go to the next section where we create the virtual hard disk. In this window, we keep the default settings and change the storage size to 30 gigabytes, which is enough for installation, updates, and tools we'll use later. Once everything looks correct, we click the Finish button. Right after that, the virtual machine appears in the VirtualBox list, and on the right side, we can see a full summary of all the settings, including memory, CPU, storage, and network configuration. This means our virtual machine has now been successfully created and is ready for the operating system installation in the next steps. Now we have a few more settings to adjust before starting our virtual machine. So here we click on the settings button at the top and a new window appears with different options on the left side. Here we first click on the System tab. Inside the System section, we look at the field called Pointing Device. We changed it to a USB tablet. We selected the USB tablet because it gives better mouse movement and smoother control inside Linux environments. So later, when we start using CentOS, the mouse will move properly without lag or jumpy behavior. After doing that, we click on the Network tab. Here on Adapter 1, you can see the network mode. By default, it is usually set to NAT, but we change it to Bridged Adapter. As soon as we select Bridged Adapter, the name field updates automatically based on the network device of our computer. Why do we select Bridged mode? Because with Bridge mode, the virtual machine behaves like another real computer on the same network. This means it gets its own IP address from the router, just like a laptop or a phone. This will help later when we want to connect to it using SSH or use it for networking practice. Next, we click on the storage section, and here you can see there is an option that says empty under the IDE controller. This means the virtual machine does not yet have an installation image attached. So now we click on the small CD icon on the right side. As soon as we click it, a small menu appears, and from this menu, we choose Create a Virtual Optical Disk. A new window opens where we can browse our system for the Linux ISO file. In this case, we select the CentOS Stream ISO file that we downloaded earlier, and then we click the Open button. After selecting it, another window shows the ISO file in the list. Here we click Choose, so VirtualBox attaches this ISO as a virtual DVD. Once the ISO is attached, you can see that the previously empty CD slot now displays the CentOS image. This means the machine is now ready to boot from the installation file. Finally, we click the OK button at the bottom to save these settings. Now that everything is ready, it's time to start the virtual machine. For this, we simply click the Start button at the top. As soon as we click it, a new window opens, which is our virtual machine screen. It's better to maximize this window so the installation becomes easier to see. Now on the screen, you can see a few options, and the first one says Install CentOS Stream 10. This is the option we want, so we select it and press Enter. After that, the system starts loading some files, and this stage may take a little time, so we just wait and let the process complete. Once the loading is finished, the first installation screen appears, and here we need to select the language we want to use for installation. The default language is English, and we will keep it as it is. After confirming the language, we click on the Continue button to move to the next step. Now a new window appears, and this screen is called the Installation Summary. This page shows all the basic settings we must check before installing CentOS. The first thing we need to set is the installation destination. So we click on it. Once it opens, you will see the storage device that we created earlier, the 30 gigabyte virtual hard disk. We click on it. To select it, we leave everything else as default and then click the Done button in the top left corner to confirm this step. After that, we return to the summary page, and now it's time to set the network and host name. So we click on the option that says network and host name. A new window opens, and here you can see the network switch is on, which means the virtual machine can connect to the internet. At the bottom of this window, there is a text box where we can type a host name. Here we type, for example, CentOS Linux, or you can choose any name you prefer, and then we click the Apply button. Once we do that, the host name updates on the right side. Now everything looks good, so we click Done to return to the summary page. Next, we move to the root account option because by default it is disabled. So we click on it, and inside this window we select Enable Root Account. Now we enter a password for the root user and confirm it in the second box. You can also see an option that says allow root SSH login with password. We check it because later when we use SSH, this will allow us to access this Linux system remotely from another machine using the root credentials. After entering the password, the system may give a warning that the password is weak, but since this machine is only for testing and learning, we don't worry about it. We simply click the Done button twice to confirm. After setting the root account, the next step is user creation. So we click on it. Here you can see some fields. First, we type the full name. For example, Imran Afzal. The system automatically creates a username based on the name. So in this example, it becomes IMf&x. Below that, you will notice two checkboxes already selected by default. This means this user will require a password to log in and also will have administrative privileges. Now we type the password for this user and confirm it in the second box. Again, if it shows a weak password warning, it's okay. We just click done twice. Now all the major settings are complete. We keep everything else as default. At this point, the system is ready. So we go ahead and click begin installation to start installing CentOS. Now the installation will take a little time, so we simply wait. Once the progress bar reaches the end, that means the installation is completed. At this point, we just click on the Reboot System button. The system will restart, and the reboot process may also take a few moments, so again, we wait patiently. After the reboot, the login screen appears, and here we can see the user account we created earlier. We click on it and type the password we set during the installation. Once the correct password is entered, the desktop interface loads for the first time. A welcome pop-up appears offering a short system tour, but since we don't need it now, we simply click the skip button and move forward. Now, the CentOS desktop is fully visible, and at the bottom of the screen, we can see a few important applications. One of them is the terminal, which is the most important tool for Linux administration. So we click on the terminal icon to open it. Here we can now see the Linux shell prompt, and here it clearly shows our logged in username and our machine host name. In our case, it shows ifzal at the rate of CentOS Linux, which confirms that our Linux installation, hostname, configuration, and user setup were all successful. Now that our system is ready, the next step is to connect this Linux machine remotely using PuTTY. PuTTY is an SSH client used to securely connect to Linux systems from Windows, and this helps us manage our server without always using the VirtualBox console. Before opening PuTTY, we first need to check the IP address of this CentOS machine because SSH works using an IP. So in the terminal, we type the command IP space A and press enter. This command displays all network interfaces and their IP addresses. Here you can clearly see that the interface named ENP0S3 has the IP address 192.168.100.242, and this is the address we will use to connect from PuTTY. Now let's open PuTTY on our Windows machine. If you don't have PuTTY installed, you can easily download it from its official website and install it, just like any normal Windows program. Once PuTTY is open, you can see this interface. At the top, there is a box where we need to type the IP address of our Linux machine. And so we type 192.168.100.242, which we found earlier using the IPA command. The port number is already set to 22, which is the default SSH port. So we leave it as it is. Below that, make sure the SSH option is selected, and in our case, it is already selected by default. After entering the IP address, we type a name for this connection under the Saved Session section. This step is optional, but it helps us remember this machine later, so we don't have to write the IP address again every time. Once we type the name, for example, CentOS Linux, we click the Save button. Now the session is saved and ready to use. Next, we click on the Open button to start the SSH connection. As soon as we click Open, a new window appears and we get a PuTTY security alert. This message is normal because it is the first time we are connecting to this machine. We simply click Accept to save the SSH key and continue. After that, a login screen appears asking for a username. Here, we type the same username that we created during the CentOS installation. In our case, its IMf&x and press enter. Then it asks for the password. We type the password and press enter again. If the login information is correct, you can now see that we are successfully connected to our CentOS machine through SSH using PuTTY. So this is a simple explanation of how to set up a virtual machine and install Linux CentOS inside VirtualBox and connect CentOS Linux machine remotely using PuTTY over SSH. In this lecture, we will learn how In this lecture, we will prepare the Linux system by installing important tools and configuring it properly to run containers smoothly. This step is important because preparing the system helps to avoid performance issues, network problems, and unexpected failures later. It also ensures that everything runs smoothly and consistently when containers are started and managed. Let's get started. For this, we first open PuTTY terminal that is already connected to our CentOS machine. Here we log into our account named IMf&x, and after entering the password, we can see that the login is successful and the system is ready to use. Let's move on. And first we install some basic packages that we will need again and again while working on the system. Tools like curl and wget help us download files from the internet. Git is used to manage and download code, and editors like Vim and Nano allow us to open and edit configuration files easily. Packages such as unzip and tar help us extract compressed files. Yum-utils is useful for managing software sources. And JQ helps in reading and understanding system data in a clean format. We use sudo here because installing software is a system level task, and normal users are not allowed to change the system by default. Using sudo gives temporary permission to perform this task safely and correctly. After pressing enter, you can see that the system starts processing the installation of these packages. Some packages are already installed and up to date, so the system skips them automatically, while the remaining packages that are missing begin downloading and installing. You can also see that required supporting packages are pulled in automatically during this process. After a short time, the installation completes successfully, which confirms that all needed packages are now properly installed and ready to use. After that, we move on to the next step and install a set of packages like contract, so cat, IP, roottc, and IP tables, which are mainly used for handling system and network communication. Here, contract helps the system to keep track of active connections. For example, when an application sends a request and waits for a response. And this is important in Kubernetes or Minikube when pods communicate with each other. And so CAT is used to pass data between two programs, such as connecting services inside pods or forwarding traffic between components in a cluster. iprootc helps control how network traffic flows, which is useful when Kubernetes manages many pods sharing the same network. And IP tables is used to allow or block network traffic. And Kubernetes relies on it to route service traffic correctly and keep pod communication secure. Let's wait until these packages are installed correctly. And after a short time, you can see that all of these packages are installed successfully. Now it's time to disable swap. Swap is a system feature that uses hard disk space like extra memory when the main memory, also called RAM, becomes full. You can think of it like a small storeroom used when your study table is full of books. The system moves some data from memory to disk so programs can keep running. This is helpful for normal computers. but it is not good for Kubernetes. Kubernetes needs to clearly know how much real memory is being used at all times. If swap is on, the system hides the real memory situation and Kubernetes gets confused. Because of this confusion, containers may become slow or stop unexpectedly. Kubernetes prefers clear and direct memory usage without any hidden space. By turning off swap, Kubernetes can make better decisions about running or stopping containers. This keeps applications stable and predictable. That is why disabling swap is an important step before running a Kubernetes or Minikube. Now it is successfully disabled. If you want to disable it permanently, this is done by editing the system startup file name /etc/fs tab so the system does not enable it again after reboot. In this command, the /etc/fs tab file is modified. The swap entry line inside this file is targeted, and that line is commented out so the system ignores it in the future. This ensures swap stays disabled even after restarting the system, which is required for Kubernetes to work properly. Let's confirm it. And here you can see that the swap value shows 0, which means swap has been successfully disabled. So now all the prerequisites are set and our system is ready for Kubernetes setup. See you in the next lecture. In this lecture, we are going to install Docker and prepare the system to run containers smoothly. Let's get started. For this, we first open the PuTTY terminal, and here we are already logged in using the IMf&x account. Now, the very first thing we do is add Docker's official software source to the system. This source contains Docker CE, which stands for Docker Community Edition and is a stable and recommended version used in most real environments. Using the official Docker source ensures we do not get an old or unsupported Docker version from the default system packages. It also helps avoid compatibility issues later with containers, Kubernetes, or Minikube. We use sudo, pronounced as sudo, because adding a software source changes system settings, and normal users are not allowed to do this. After pressing enter, you can see that the Docker repository is successfully added to the system and is ready for the Docker installation. Let's move on and install the main Docker components needed to run containers on the system. Here we use Docker CE, which is the Docker engine that actually creates and runs containers. Docker CE CLI is the command line tool that we use to give instructions to Docker, and container.io is the background service that handles container execution and lifecycle. All three work together to make Docker function properly. After pressing enter, the system starts installing these Docker components. So we wait for the process to complete. After a short time, you can see that the installation finishes successfully, which means Docker is now properly installed on the system and ready for use. Now it's time to enable and start Docker, and we do both in a single command. This step makes sure Docker starts running immediately and also starts automatically every time the system boots. Let's verify it now. Here we use the no pager option so the output is shown directly on the screen without opening it in scroll mode, which makes it easier to read. In the output, you can clearly see that the Docker service is loaded, enabled, and active. This confirms that Docker is running properly and is also set to start automatically after a system reboot. With this confirmation, Docker is successfully installed, started, and ready to be used. Let's move on and add the user to the Docker group because by default, Docker commands require special permission. Without this step, every Docker command would need sudo, which is not convenient for daily work. By adding the user to the Docker group, we allow the user to run Docker commands directly as a normal user. This makes working with Docker faster, cleaner, and more comfortable, especially when using Docker frequently with Kubernetes or Minikube. After that, we refresh the user's group membership so the changes take effect immediately. This step allows the current session to recognize that the user is now part of the Docker group. Without doing this, we would need to log out and log back in. After this, Docker commands can be used without sudo in the same terminal session. Now it's time to test Docker properly. For this, we fetch the hello world image using the Docker command, which is a small built-in test image provided by Docker. The hello world image is used only to confirm that Docker can download images, create a container, and run it successfully. Here, the RM option is used, so the container is removed automatically after it runs, keeping the system clean. After pressing enter, you can see that Docker first checks if the hello world image is already available on the system, and since it is not found locally, Docker automatically downloads it from Docker Hub. Once the download is complete, Docker creates a container from this image and runs it. After that, you can clearly see the output message that says, "Hello from Docker," which confirms that Docker can pull images, create containers, and run them successfully. This final message proves that Docker is installed correctly and working as expected. Finally, let's check the Docker version, which is helpful for us to confirm what is installed and to make sure it is compatible with Kubernetes or Minikube. Here you can see that the Docker Engine community version is installed and the version we are using is 29.2.1. This output also shows both the client and server details, which confirms that Docker is running correctly. Knowing the exact Docker version helps during troubleshooting and ensures we are working with a supported and stable setup. In this lecture, we are going to install Minikube to run Kubernetes locally on our system. Let's get started. For this, we first open the PuTTY terminal, and here we are already logged in using the IMf&x account. Now, the very first thing we do is download the Minikube setup file to our system. For this, we use curl, pronounced as curl, which helps us to download files directly from the internet using a link. We are downloading the latest Minikube version, so we don't need to worry about outdated features or fixes. Here, the Linux-AMD64 part means this file is made for Linux systems running on 64-bit machines. After pressing enter, you can see that the download starts and the file size is around 128 megabytes, so it takes a little time to complete. We simply wait until the download finishes. After some time, the download completes successfully, which means the Minikube file is now available on our system and ready to install. So let's install it by using the name of the downloaded file, which is minikube-linux-amd64, and place it in the location /usr/local/bin. This location means the program will be available system-wide and can be run from anywhere in the terminal without typing the full path. We use sudo, pronounced as sudo, because copying files into this location requires system permission. After pressing enter, it gets installed immediately, and you do not see any message because this command runs silently when it completes successfully. If there is no error shown, it means the file was copied and installed correctly. This is normal behavior and indicates that Minikube is now placed in the correct location and ready to use. let's move on and check which Minikube version we are using because it helps us confirm that Minikube is installed correctly and is suitable for our setup. Here you can see two outputs, and the first one shows the Minikube version number, which tells us the exact release we are running, and the second one shows the commit information, which identifies the exact build of that version. This commit detail is useful when comparing behavior, fixing issues, or checking documentation because it confirms the exact code build that is running on the system. Till now, we have installed all the prerequisites, then installed Docker, and after that installed Minikube. Now we can create containers using Docker and use Minikube to run a local Kubernetes cluster on our system. However, one last and very important tool is still missing, which is kubectl, pronounced as kube control, and it is used to control and manage the Kubernetes cluster. So now it's time to install kubectl so we can communicate with Kubernetes and manage our workloads properly. Let's get started. For this, we first open the PuTTY terminal, and here we are already logged in using the IMf&x account. Now, the very first thing we do is download kubectl, and for this we use a URL from dl.k8s.io, which is the official download location provided by Kubernetes. This URL always points to trusted Kubernetes files and automatically selects the latest stable version, so we don't have to hard code a version number. The URL also clearly shows that the file is for Linux and 64-bit systems, which matches our setup. Using this official URL ensures security, correctness, and compatibility with the Minikubes and Kubernetes. After pressing enter, you can see that the download starts and the file size is around 55 megabytes, so it takes a little time to complete. We simply wait until the download finishes. After a short while, the download completes successfully, which means the kubectl file is now downloaded and ready to install. Next, we install it using this command, where -m is used to set permissions for the file. The value 0755 means the owner can read, write, and run the file while others can read and run it, which is required for system commands. We install it into /usr/local/bin, which means the command becomes available to all users and can be run from anywhere in the terminal. After pressing enter, you can see that nothing is shown on the screen, which means there is no error. This command completes silently, which indicates that kubectl has been installed successfully in the correct location and is ready to be used. Finally, we check the version to verify the installation, and here we use the client option because at this stage, we are only checking the kubectl tool itself and not connecting to any Kubernetes cluster yet. In the output, you can see the first value shows the kubectl client version, which tells us which Kubernetes command line version is installed. The second value shows the customized version, pronounced as customize, which indicates the built-in tool used for managing Kubernetes configuration files. Seeing both values confirms that the kubectl is installed correctly and ready to work with Minikube. Hey folks, we have completed the setup and now it's time to create our first Kubernetes cluster using Minikube. In this lecture, we will start the cluster and prepare the environment to run and manage Kubernetes resources locally. Let's get started. For this, we first open the PuTTY terminal, and here we are already logged in using the IMf&x account. To start the Kubernetes cluster, we type the command minikube start driver equals to Docker. Here, driver equals to Docker means Minikube will use Docker to create and run the Kubernetes cluster instead of a virtual machine. This allows the cluster to run inside Docker containers, which is faster, lighter, and easier to manage on our system. After pressing enter, Minikube starts the cluster creation process step by step. First, it shows a memory warning because we are using 4 gigabytes RAM, which is the minimum required. But this is only an informational message and the cluster works fine. If you use 5 gigabytes or more RAM, this message will not appear. Then Minikube downloads the preloaded Kubernetes images, such as preloaded dash, images dash K8s, which contain the basic Kubernetes components needed to run system services and pods. After that, it downloads the KIC base image from gcr.io/K8s-minikube/KIC base, which is the main base image used to create the Kubernetes node inside Docker. The time taken for these downloads depends completely on your internet speed. So slower internet means more time. After this, Minikube configures networking, prepares Kubernetes components, enables default storage options, and finally shows a message confirming that the cluster is successfully created and ready to use. Now, our first cluster is successfully created. Let's move on and verify it. For this, we check the Minikube status, which shows whether the cluster, node, and core components are running properly. After pressing enter, you can see the complete status of the Minikube cluster. The control plane shows that the main Kubernetes node is created and active, which means the brain of the cluster is working. The host running status confirms that Minikube itself is up and running on the system. The kubelet running message means the service that manages pods and containers on the node is working properly, like a manager making sure everything runs as expected. The API server running status shows that the central communication service of Kubernetes is active, which allows kubectl commands to talk to the cluster. Finally, kubeconfig configured means kubectl is correctly connected to this cluster, so we can now create and manage Kubernetes resources without any issue. Then we check the cluster information to make sure Kubernetes is reachable and working correctly. After pressing enter, you can see an HTTPS URL with an IP address and port, which shows where the Kubernetes control plane is running. This IP address is the internal network address used by Minikube, and the 8443 port is the secure port where the Kubernetes API listens for requests. For example, when you run a kubectl command like creating a pod, it sends the request securely over HTTPS to this IP and port, and the API server responds back. You can also see core DNS running at another secure address, which means name resolution inside the cluster is working, so pods can find each other by name instead of IP. Seeing this output confirms that the cluster is active, reachable, and ready to manage applications securely. Hey folks, we have created our first cluster and now it's time to verify it and confirm that everything is running correctly and ready for use. Let's get started. For this, we first open the PuTTY terminal, and here we are already logged in using the IMf&x account. Let's move on and verify the cluster using the command kubectl get nodes -o wide, because this command helps us to confirm that the Kubernetes cluster is running and accessible. The get nodes part is used to ask Kubernetes for the list of machines that are part of the cluster, which tells us whether the node is ready and healthy. The dash O wide option is used to show extra details, such as the node's internal IP address, operating system, and container runtime, which helps us understand how the cluster is configured. When this command runs, kubectl uses kubeconfig to know which cluster to connect to and how to reach the control plane securely. Kubeconfig is a configuration file that already contains the cluster address access details and security settings. Because Minikube has already set kubeconfig for us, kubectl successfully connects, fetches the node information, and confirms that our cluster is working correctly. After pressing enter, you can see the full details of the Kubernetes node in a clear table format. The name shows Minikube, which means this is our local cluster node. And a node is simply a machine where Kubernetes runs and launches applications, just like a computer that does the actual work. The status ready means the node is healthy and able to run applications, just like a machine that is powered on and ready to work. The roles control plane tells us this node is acting as the main controller that manages the cluster. The age shows how long the cluster has been running, and the version v1.35.0 confirms which Kubernetes version is installed. The internal IP is the private IP used inside the cluster for communication, while external IP none is normal for local clusters like Minikube. The OS image and kernel version show the operating system and kernel used by the node, and container runtime Docker confirms Docker is being used to run containers. After checking the node information, let's move on and verify the pods, which are the smallest working units inside a Kubernetes node. A pod is where applications and system services actually run, just like apps running inside a computer. For this, we use the command cube ctl get pods -a, where -a means we want to see pods from all namespaces, including system ones. After pressing enter, you can see a list of pods running in the kube-system namespace, such as et-cd, kube-api server, controller-manager, scheduler, and core DNS, which are essential services that keep Kubernetes running. The status running and ready 1/1 show that each pod is healthy and working properly. This confirms that the internal components of Kubernetes are running correctly inside the node, which means the cluster is fully functional and ready to run applications. Let's move on and verify the list of Minikube add-ons. For this, we use the command Minikube add-ons list. An add-on in Minikube means an extra built-in feature that provides additional services to the Kubernetes cluster, such as storage, networking, dashboards, or monitoring. We check the add-ons to understand which extra features are already available and which ones are active in our cluster. After pressing enter, you see the output in a table format where each add-on is listed with its status. Here, enabled means the feature is active and ready to use, while disabled means it is available but not running. For example, default storage class and storage provisioner are enabled because Kubernetes needs them to automatically create storage when an application asks for disk space. In simple words, checking add-ons is like checking which tools are already installed in a toolbox, so you know what is ready to use and what you may need to enable later. Next, let's move on and create our first application inside the Kubernetes cluster so we can clearly see how things work in real time. First, we create a deployment using kubectl create deployment and nginx dash image equals to nginx command. Here, deployment means we are telling Kubernetes to manage an application for us. Nginx is the name we give to this application. The image name, nginx, means Kubernetes will download the ready-made nginx web server image from the container registry and use it to run our app. After pressing enter, Kubernetes confirms that the deployment is created, which means the request was accepted successfully. Next, we run kubectl get deployments to check the status of this deployment. At first, you may see 0 over 1, which simply means Kubernetes has created the deployment, but the container is still starting. After a short moment, when you run the same command again, it shows a 1 over 1, which means one container was requested and one container is now running successfully. This confirms that Kubernetes has finished setting up the application. After that, we use a kubectl get pods -o wide command to see the actual running pod. A pod is the smallest running unit in Kubernetes, and it contains the nginx container. In the output, you can see the pod name, its status running, and ready 1 over 1, which means the container inside the pod is healthy. You also see the IP address, which is the internal address given to this pod, and node minikube, which tells us the pod is running on our minikube node. So what we do here is we create our first application inside the Kubernetes cluster using a deployment. We ask Kubernetes to download the nginx image and run it as a container. The nginx image is used because it is a very lightweight and popular web server image that starts quickly and is perfect for testing. Kubernetes then creates a deployment to manage this application for us. After that, it automatically creates a pod to actually run the nginx container. Then we check the deployment to confirm it is created and fully ready. After that, we check the pod to make sure it is running without any issues. This confirms that our cluster is working correctly and can run real applications.